Hey everybody, just me again. Alright, so here's your second video for the year. This first unit that we're studying, which if you look at your syllabus is called The Structure of Matter, is actually a combination of the first two chapters in your book. So chapter 2 is termed The Atoms, Molecules, and Ions. Obviously we quickly went through chapter 1 with the first day discussion that we had here in class, and then the first video that you watched at home. So today's discussion is going to take us a little bit into the development of the idea of the atoms, molecules, and ions that we're familiar with. All right, so today we're only talking about sections 2.2 through 2.4 in your book. We got really three important laws that are going to focus us in chemistry that are kind of all-encompassing. You'll see these happen throughout the chapters. Number one is the law of conservation of mass, indicated by Antoine Lavoisier. He's a French chemist. And that simply mass is neither created nor destroyed. And then Proust, another chemist, defined what's called the law of definite proportion, which just simply says a given compound always contains exactly the same proportion of elements by mass. So essentially what that means is, water is always H2O, so it's always got two H's, one O, and those things contain exactly the same proportion of elements by mass. Okay. Let's continue that to the law of multiple proportions, and that says that when two elements form a series of compounds, the ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. So again, it just says that when you are combining compounds, those compounds essentially combine with one another in equal ratios. The big ones that we focus on throughout the series of chemistry are the law of conservation of mass from Lavoisier and the law of multiple proportions from Dalton. So Dalton had an atomic theory that he came up with and published this around 1808. And this atomic theory has a couple of different points, not all of them still holding valid today, but at the time they were groundbreaking as chemistry was kind of dead for a couple of decades, and he kind of brought it back to the forefront. Dalton said that each element is made up of tiny particles called atoms. It seems easy for us, but it wasn't intuitive to chemists back in the early 1800s. These atoms of a given element are identical. The atoms of different elements are different in some fundamental way or ways. Now we know that this isn't exactly true because we have things that we like to call isotopes. Okay, isotopes are taking hydrogen, for example. A typical hydrogen atom has one proton and it has one neutron. Okay, I'm sorry, it's 0 neutrons, not one neutron. Let me erase that. There we go. All right, an isotope of hydrogen that has one proton and one neutron actually exists. And we actually call this hydrogen, but it's got a different name. We call it deuterium. So this is an isotope. They're both hydrogen. They just differ in neutrons. So atoms of a given element are almost identical. They're always identical in the number of protons that they have, but they can differ in the number of neutrons that they've got, and that's where we get the idea of isotopes. To continue with Dalton's atomic theory, it says chemical compounds are formed when atoms of different elements combine with each other, and a given compound always has the same relative numbers of atoms and types of the atoms. And this still holds true today. So again, when we're thinking about water, we're thinking H2O. Okay? This is an extension of his idea of the law of multiple proportions. And this is a biggie now. He said that chemical reactions, when things explode, when they blow up, when they change, chemical reactions involve the reorganization of the atoms. Okay, this is a chemical change. Okay, this isn't like boiling or freezing or melting. A chemical change takes the atoms in a particular compound and it totally rearranges them. So if you would electrify water, okay, you take H2O and you actually rearrange it. You make hydrogen, H2, and separate oxygen, O2. That's a chemical reaction. So it changes the way that the atoms are bound together. But in this type of idea, those atoms themselves are not changed. They stay the same. It would take a nuclear process in order to change those. So let's kind of go back to this concept check idea. Which of the following statements regarding Dalton's atomic theory are still believed to be true? There they all are. Take a minute to look at them. Okay, and the green ones are still remaining to be true. All atoms of a given element are identical. We know that that can be different because of the ideas of isotopes. And number 4, atoms are indestructible. They're not. The nuclear plants, atomic bombs, and such have proven otherwise. All right, so let's figure out how we know so much about the atom. We have gone over this stuff in previous chemistry courses. I'm just going to skim it really quick. So the parts of the atom, the electron, the proton, and the neutron, where do they come from? In the late 1800s, J.J. Thomson came around and he postulated the existence of electrons using something called a cathode ray tube. He determined the charge to mass ratio of an electron. So he didn't determine how big the electron was, and he didn't determine how much charge there actually was. He determined the ratio for those two. But that's important because if we find out either of the others, the charge or the mass, then we know both. Okay? So he knew that the electron existed, and he then found a charge to mass ratio. His other thought was that, okay, if there's these negative things within this quote-unquote atom, there must be positive things because, you know, with every negative you have to have a positive. They balance each other out. If that weren't the case, everything would be negative and nothing would ever exist. Okay, so he didn't know what these positive things were, but he pretty much thought that they were around somewhere. And here's a picture of the cathode ray tube. The idea of the cathode ray tube is that electrons are sent throughout the tube. There is a magnet on either side of the tube, and the electrons, which I'm drawing here on the screen, are repelled. And by knowing how much they are repelled and how strong that magnet is, again, he was able to find that charge to mass ratio for the electron. And that went a long way in the discovery of this particular subatomic particle. Okay? So now, we look at the three types of rays emitted by radioactive elements. Now, this is one of the things that led us to understand, we know that elements can actually change. This kind of disproving that fourth point of Dalton's law, that if we took a substance like uranium, if we mined some uranium and put it inside of something, and we allow it to actually emit radiation, we'll notice that the uranium not only changes over time, but also that it emits particles in different types of particles. And we define these as alpha, gamma, and beta particles from top to bottom there on your screen. Okay, we'll get more into this when we talk a little bit more extensively about nuclear chemistry. All right, so now we've just disproven that fourth point of Dalton because that element would change. If we let this actually react long enough, the uranium compound that's sitting inside of this lead block would actually become lead itself. That would take quite a while, though. All right, so how did we find out the actual charge and the actual mass of the electron? It came to Robert Millikan in 1909 to do that. So he performed experiments involving charged oil drops. He charged oil, like a spray of oil, as it passed down through essentially what looked like a coffee can. And then those droplets, those tiny, tiny droplets of oil became charged with electrons. And he determined the magnitude of the charge on a single electron. So remember what I said before. Thomson had the ratio, the charge to mass ratio. He didn't have the exact charge. He didn't have the exact mass. And if we found either of those two, well, it would be easy to find the other one. Millikan, from his oil drop experiment, determined the magnitude of the charge on a single electron, and thus he's able to calculate the mass of the electron. All right, and lastly, Ernest Rutherford. So Rutherford then came and explained the nuclear atom. Rutherford had an experiment called the gold foil experiment, in which he was able to shoot particles at a nucleus, and what happened is these particles hit the nucleus and they bounced off in different directions. This told him that the atom wasn't just a plum-pudding cloud-like structure. It actually had a dense center, and that center had to be positive since the electrons, or in this case, not the electrons, since the alpha particles, or helium particles, were bouncing off, those alpha particles being positive themselves. So what he concluded was that there's this dense center of charge and that electrons traveled around the nucleus at a large distance. All right. So that's kind of a synopsis of our early view of the atom and how we've come to understand that there is a nucleus, that electrons spin around it, and where those experiments have led us. If you want a little bit more information on how those experiments run, pictures or diagrams of that, you always can come see me. All right, that's it.